Okay, in this lecture we're going to begin the section 3.8 material on forced vibrations. So what we had seen in the previous section is that the equation of motion for a mass spring system subject to an external force given by some function capital F of t is of the form my double prime plus by prime plus ky equals f of t, where m is the mass, b is the damping coefficient, and k is the stiffness of the spring, where f of t is our external force. So a problem of particular interest is the case where we have a forcing function which is periodic. So let us suppose that the external force is a periodic function. So let's say it can be expressed as f of t is some constant f naught times cosine of gamma t, where f naught is some positive constant, which is the amplitude of our force, and gamma is some positive constant, which would be the frequency of the force. So in this case, our equation of motion would have the form my double prime plus by prime plus ky is f naught cosine of gamma t. So what we have here is a second order linear non-homogeneous equation with constant coefficients m, b, and k. And we've seen that for these non-homogeneous equations, the general solution would be of the form y of t is equal to y sub h of t plus capital Y of t, where y sub h, our homogeneous solution of a second order linear equation, would be of the form c1 times y1 plus c2 times y2. So this is our homogeneous solution, or solution of the corresponding homogeneous equation. And when we talk about mass spring systems, the homogeneous solution is given a particular name. It is called the transient solution. And we'll see in this section why we call it a transient solution. And our particular solution, capital Y of t, could be determined by using, say, the method of undetermined coefficients. We see that our forcing function, f of t on the right-hand side, is some constant times cosine of gamma t. So for our particular solution, we could consider something of the form a times sine of gamma t plus b times cosine of gamma t. And this would be a particular solution of our non-homogeneous equation. And this is referred to as the steady state solution when we talk about mass spring systems. So again, the homogeneous solution is referred to as the transient solution, and the steady state solution refers to our particular solution. And to solve for the constants a and b in our particular solution, we could find our first two derivatives and substitute into our non-homogeneous equation, and we obtain the following. By substituting that expression for the particular solution into our non-homogeneous equation, the coefficients are given by a is f naught b gamma over k minus m gamma squared quantity squared plus b squared gamma squared. And b is given by f naught times k minus m gamma squared over k minus m gamma squared quantity squared plus b squared gamma squared. So our particular solution could be rewritten instead of a sum of sine and cosine of gamma t As we did in the previous section by making use of trig identities, we could rewrite our particular solution as a single cosine wave, which would have the form f naught over the square root of k minus m gamma squared quantity squared plus b squared gamma squared times cosine of gamma t minus delta, where delta satisfies the equation tangent of delta is equal to b over a, and the value of delta would be determined by the signs of a and b. So we see here that our particular solution is also periodic, and it has the same frequency as the forcing function. Same frequency gamma. However, it is out of phase with the forcing function because of that delta shift which was applied. And the magnitude of our particular solution differs from the forcing function by a factor of 1 over the square root of k minus m gamma squared quantity squared plus b squared gamma squared. So we see here that when we compare the magnitude of our forcing function, which was f naught, and the magnitude of the particular solution, they differ by this factor 1 over that square root term. So this factor that they differ by is referred to as the frequency gain, or gain factor, since it represents the ratio of the magnitude of the response of our system to that of the input force. So let's think about this frequency gain, or gain factor, in a bit more detail. We see that it depends on the frequency of our external forcing function, gamma. So in general, the amplitude of our steady state solution will depend on the frequency, which we were calling gamma, of our external forcing function. In particular, the amplitude of our steady state solution is given by f naught times m of gamma, where m of gamma was that frequency gain, or gain factor, 1 over the square root of this expression. So we can think of this gain factor as a function of gamma. And let's think about how this gain factor depends on gamma. So to see how this would depend on gamma, let's consider the graph of this gain factor, m of gamma. So the graph of this function is called the frequency response curve, or sometimes the resonance curve of our system. And this graph illustrates how a given system would react to periodic inputs of different frequencies. So let's think about sketching this frequency response curve. So to sketch this, let's first note that when gamma is 0, that is, if our forcing function was a constant, f naught, then our frequency response would be 1 over k, 1 over the stiffness of the spring. So the larger our stiffness of the spring, that is, the more difficult it is to move, we would have a smaller frequency response. And as gamma approaches infinity, then m of gamma, our frequency gain, approaches 0. Now, to get a little more information about the shape of this frequency response curve, we could look at the derivative of this m of gamma function, and we obtain the following expression. And so it follows that m prime of gamma is equal to 0 if and only if gamma is either 0 or gamma is equal to gamma sub r, which is given by the square root of k over m minus b squared over 2m squared. We can see this by setting our derivative equal to 0. Well, in order for the numerator to be 0, since our mass is non-zero, either gamma has to be 0 or the expression in the square brackets has to be 0. And so solving that expression for gamma, we find this square root of k over m minus b squared over 2m squared. So in the case that our system is overdamped or critically damped, the derivative m prime of gamma is equal to 0 only when gamma itself is 0, since that gamma r value would have a negative under the square root, or 0 under the square root in the case that this system would be overdamped or critically damped. And if this system is underdamped, then m of gamma has a maximum at this gamma r expression. So this value, gamma r, is called the resonance frequency for our system. And if our system is stimulated by an external force that has that frequency, we say that the system is at resonance. So this gamma r, which we call the resonance frequency, would be the frequency of the forcing function, which maximizes the magnitude of our steady state solution, our particular solution. So here, using this information, we could sketch our frequency response curve. So here in the figure below, we have graphed several frequency response curves for a system where the mass and stiffness are both equal to 1, and looking at varying damping coefficients, B. So we see that when gamma is 0, the value of m is 1 over k. So if k is 1, we have 1. And then as gamma increases, we see these curves are approaching 0. They're decaying the larger that gamma becomes. And then we have these peaks which are occurring in my frequency response curve at the resonance frequency when gamma is equal to gamma r. And here these different curves that we're showing represent or correspond to different damping coefficients, B. And so here we have, for smaller B values, that is, if less damping or less friction is present, a larger frequency response. And the larger that B becomes, we see the magnitude of our frequency response decreases. So here notice that as our damping coefficient B is approaching 0, the maximum magnitude of this frequency gain is increasing. So then a question of interest would be, what happens if there is no damping? What if B, our damping coefficient, is equal to 0? So that's what we're going to consider next in the second part of